Hello and welcome to this video where we'll delve into the fascinating science that allows F1 cars to perform at the pinnacle of motorsport. The technical aspects that define these high-performance racing machines will be explored, from downforce to drag, lift, and the other complex components of an F1 car. This video will provide a comprehensive understanding of the science behind its ridiculously high speeds. One of the most critical aspects of an F1 car is downforce. Downforce is the force that pushes the car down into the track, creating more grip for the drivers along with maintaining the stability of the cars as they navigate through high-speed turns. On a track where there are several corners, team engineers may modify their car to increase downforce, leading to higher cornering speeds. On the other hand, on a track with more straights, they might modify their car in order to reduce downforce for higher straight-line speeds. Take the Monaco track, for example. There is minimal straights and several corners. Therefore, the F1 teams may change the aerodynamics of their car to generate more downforce. On the contrary, a track like Bahrain, there are more and longer straights, and the generated downforce of the cars may be lower. However, this downforce comes at a cost, which is drag. Drag is the wind resistance that hinders a car's forward progress. Minimizing drag is a constant challenge for F1 teams, as it directly impacts the car's top speed, especially along the straights. Parts on the F1 car like the rear wing, which we'll talk more about later, can generate a lot of downforce. However, in turn, the aerodynamics of the car is altered, leading to an increase in drag, slowing the car down on straights. Lift, conversely, poses a significant threat to downforce. It is the upward force that could potentially lift the car off the track. This is where the angle of attack is introduced. Angle of attack refers to the angle at which the incoming fluid, air, is hitting the object in motion, often a wing of an airplane, or in this case, the front wing of an F1 car. It directly impacts the lift production of the object when it is moving through this fluid. As seen in the picture on the screen, the movement direction of the relative airflow is relative to the wing of the plane. A perfect angle of attack is needed to be calculated by the F1 teams in order to minimize lift and drag. To understand these principles better, we must dissect the F1 car. From the intricacies of the front wing to the precision of the rear wing, every component serves a distinct role in shaping airflow, enhancing downforce, and minimizing drag. The performance of these vehicles is all due to the innovative technology used to design and craft these components, where everything is calculated to the last minute detail. However, the rear wing might be one of the most important outside features of the car because it is involved in a system called DRS. The drag reduction system, or DRS, is a fascinating feature of F1. This system involves a flap on the rear wing opening as seen in the image to momentarily decrease drag and increase the speed of the car. The car is able to travel approximately 20 to 30 kilometers faster when DRS is enabled. However, it is only available along the straights on the circuit. The efficiency of DRS is contingent on the quality of air, referring to clean air or dirty air surrounding the car. Clean and dirty air refers to how streamlined the air is when the car is traveling through the fluid. When a car is on a straight by themselves, the air is undisturbed, clean, creating high downforce and enhancing cornering speeds. Dirty air is experienced by a car that is following closely behind another car. Since the air is disturbed by the car in front, the aerodynamics cannot be optimized in the same way. This is because the parts on the car that generate downforce rely on predictable and undisturbed air. However, when a car is following extremely close behind another car, a slipstream is created which reduces the drag created by the front and rear wing, allowing for quicker straight line speeds. To grasp the application of DRS, let's consider a hypothetical race scenario. Picture two F1 cars engaged in a high-speed duel down a straight. The pursuing driver deploys DRS, resulting in a sudden surge of speed. These pictures from a DRS experiment show where the wind resistance would impact the rear wing if one car had DRS enabled and the other car didn't. From the pictures, there is more flour present in the rear wing flap when it is closed, meaning there is more drag created, slowing the car down. With the rear wing open, less flour hits the rear wing, meaning less drag and a higher top speed. As we conclude this video, we've explored the intricacies of Formula One aerodynamics, from the vital downforce that maintains control to the ever-present drag and the threat of lift. These complexities highlight the relentless pursuit of perfection in this high-stake world of Formula One. I encourage you to follow the sport more closely and really focus on the behind the scenes. This will give you a whole new perspective of the sport and may make you like it even more.